Okay, welcome back to our Calculus 3 class notes. We're now on page 53 and in section 14.4, and we're looking at the chain rule. And on this page, we're looking at the chain rule for 2 independent variables and 3 intermediate variables. So first, when will we ever have a function like this? Well, one example might be if we are interested in the temperature, W, which is f of x, y, z on the Earth's surface. We might prefer to think of x, y, and z as functions of the variables r and s that give the points longitudes and latitudes. So if x is g of rs and y equals h of r and s and z equals k of r and s, we could then express the temperature as a function of r and s as a function so it'd be of r and s, with the composite function w equals f of g of r of s, h of r of s, and k of r of s. In any event, I just wanted to give you, why would we see a function like this? Well, there's lots of reasons we see a function like that. So suppose that this is exactly our scenario. That is, w equals f of x, y, z, x equals g of r s, and h equals h of r and s, and z equals k of r and s. We then might be interested in the 2 partial derivatives, partial w with respect to r and partial w with respect to s. So again, the easiest way to get these, or to think about these, is to think of this branch diagram. So think about, if we want partial of w with respect to r, I got to get from w to r, all the different pathways I can do that. So I need to go from w through x to r, and from w through y to r, and then from w through z to r. So partial w with respect to r is partial w with respect to x times partial of x with respect to r, plus partial w with respect to r times partial of y with respect to r, partial w with respect to y, sorry, and then plus partial w with respect to z times partial z with respect to r. So there's the formula for the chain rule for the partial w with respect to r, and similarly you get the same thing for partial w with respect to s. So let's find those guys in terms of r and s. If w equals x plus 2y plus z squared, and let's say that x equals r divided by s, y equals r squared plus natural log s, and z equals 2r. So partial of w with respect to r equals partial of w with respect to x, which is 1, times partial of x with respect to r, which is 1 over s, plus partial of w with respect to y, which is 2, times partial of y with respect to r, which is 2r, plus partial of w with respect to z, which is 2z, times partial z with respect to r, which is 2. So I get 1 over s plus 4r plus 4z. Now I need to get everything in terms of r and s, so the only thing I need to substitute back in here is z equals 2r. So I put that right there. So I end up with 1 over s plus 12r, and if I'd like to write that as one fraction, my common denominator is s. So partial w with respect to r is 1 plus 12rs divided by s. Similarly, if I want the partial w with respect to s, that's partial w with respect to x, which is 1, times partial of x with respect to s, which is minus r over s squared. And then partial of w with respect to y, which is 2, times partial y with respect to s, which is 1 over s. And then partial w with respect to z, which is 2z, times partial z with respect to s, which is 0. So I just get minus r over s squared plus 2 over s. Common denominator is s squared, so I get the 2s minus r over s squared.